Hi, I'm Nitish Jolly, a PhD student from Peace Lab in Arizona State University. I'm pursuing my PhD program under the guidance of Professor Ayan Malik. I'm working on a research project uh, in collaboration with CoolCAD, which is funded by NASA. It is on high temperature power electronics, basically silicon carbide modular power conversion platform that we have built over here. It's a non-inverting buck boost topology, but modified topology, so that we can reduce the output capacitance value, because capacitance is hard to realize at a temperature more than 400 degrees Celsius. So, coming to the problem statement. So the problem statement of my project is to build a DC-DC power conversion unit for harsh space environment. Typically, the temperature ranges from greater than 400 degrees Celsius and a high radiation level. So the topology that we have chosen is a silicon carbide based non-inverting buck boost converter, as the conventional power conversion unit is not feasible for Venus mission, because the temperature is greater than 400 degrees Celsius and capacitance requirements is not feasible, because building such a bulky capacitor, which is around 100 microfarads, is not possible at that temperature. And conventional switching devices are incapable of its normal operation, so we have to use bare dies in that case. And obviously the conventional FR4 dielectric material and the conventional alloys soldering are not capable of withstanding that high temperature. So the modified non-inverting buck boost topology, um, with the output side LC low pass filter, is basically a topology having 4 switches, which is basically 2 half bridges and 1 main inductor, along with a filter inductor at the output side and a filter capacitor at the output side, and then a load. So the solution that we have proposed is fabricating a silicon carbide half bridge with making direct bonding with the PCB, and also the uh, accurate parasitic modeling is done along with the gate charge path control for synchronous switching action, because we are using two switches in parallel for realizing just one switching block. And so as to meet the capacitance value at this high temperature, the LC pi filter is used. Also the MOSFET bare die wire bonding technology is also used, and ceramic PCBs instead of FR4 material is used along with the silver alloy. So to optimally design the main inductance and the filter inductance along with the capacitances uh, for the LC pi filter, we have to incorporate the worst case scenario, which is the voltage conversion from 28 volts to 30 volts at 200 watts of power. So at that worst case, the best feasible inductor, main inductor, is 100 microhenries, and the filter inductor is around 150 microhenries, along with the filter capacitor of 0.7 microfarad and 0.54 microfarad for the output capacitor. So as you can see, the required capacitance value is decreased from around 100 microfarad to just around 2 microfarads of capacitance, which can be easily realized at a temperature of more than 250 degrees Celsius by yeah. And along with that, we have also characterized the inductances with the change in temperature ranging from 0 to greater than 200 degrees Celsius. And we see the change in the inductance by checking the the peak-to-peak current ripple. So the developed prototype consists of 4 switching blocks, each consisting of 2 switches, and each switching block consists 1 gate driver and 1 power supply. Along with that, we have the digital signal processor from Texas Instruments. It is a dual core processor which sends the PWM signals and also does the deadband modulation. Along with that, we have a main inductor which is L1, and the filter inductor which is L2, and we also have provisions to alter the drain leads by externally, so as to mitigate the mismatch between the parallel switches. And these are the table represents the design specifications, and we have a steady state results for this converter as well.
Cool. So this is my hardware prototype, which is a non-inverting buck boost converter with a LC filter at the output side, so as to reduce the output capacitance requirement. And this is the main inductor, as well as the magnesil cores were also tested as a main inductor. So right now we have made an air core inductor, so as to realize a main inductor for 400 degrees Celsius application. And so coming to the hardware, these are 4 switching blocks, and each switching block contains 2 switches in parallel, 2 silicon carbide MOSFETs in parallel, and the gate IO circuitry is a simple gate IO for each switch. And as you can see, this is the input supply to the buck boost converter. It goes to the half bridge leg, and it is connected to the main inductor, and the main inductor is connected to the output side half bridge, and the output side half bridge is connected to a LC series connected filter, which is connected to the output of the converter. And we also have a DSP, digital signal processor from Texas Instruments, that sends PWM signals to the silicon carbide devices. Okay, now I'm gonna run the converter. The voltage conversion will be from 160 volts input to 48 volts output at 200 watts of power. Alright, let's stop the video and turn off the supply. Okay, as you can see, the top two waveforms are the voltages of the switching node. Basically, the switching node voltage with respect to the power ground, and this switching node voltage to the power ground, which represents the VDS of the bottom 2 switches. And so this voltage level should be around 160 volts, and this should be around 48 volts. And the output voltage, as you can see, VRMS is around 48 volts. And the third waveforms shows the inductor current with a duty ratio of 24%, so as to get that at a switching frequency of 100 kilohertz. As you can see, the peak to peak ripple is very high in this case, because the air core inductance that I could realize with this was very low, around 34 microhenries. And my plan was to shrink this magnetics by wounding 2-3 double layering or triple layering the air core inductor, so as to get much higher inductance and reduce the peak-to-peak ripple in the inductor current. And right now the RMS value of the inductor current is around 6.5 amperes, and the efficiency of currently is relatively lower than the expected value because of the low inductance is around 93%. Thank you.